Hello students, welcome to today's session on Pascal's law and Bernoulli's principle from properties of matter and fluid mechanics. So yes, Pascal's law. So we know that there are certain laws of Newton which were describing the rectilinear motion on the ground and on the plane. Likewise, there are certain scientists and physicists who have deduced the laws which the fluids possess. So the first law was given by Pascal, and Pascal, if the pressure in a liquid is changed at a particular point, like if you are trying to change the pressure you are exerting over a liquid surface, the change is transmitted to the entire liquid without being diminished in magnitude, which also means that if there is this vessel with a volume of, you can consider this volume to be 3 volume. Yes, 3V is the volume of this vessel, and one is trying to exert a pressure of, let's suppose, 19 Newton. So where you are applying the pressure on the upside or the surface of the liquid, but this pressure is getting equally transmitted over the entire liquid in total. So it's not like you are just facing the magnitude of 19 Newton on the very superficial level, but also at the bottom base of the vessel. So that's what you call for Pascal's law. And without diminishing the magnitude, that means the entire 19 Newton is getting felt by the entire liquid. Yes. Then Pascal's law can be stated in these following ways, like the pressure in a fluid at rest is same at all points if the gravity is ignored. Like if you suppose that there is a no gravity space, is assumed, then the pressure in a fluid at rest is same because there is no gravity. So because there is not a gravity which is multiplying the mass to the acceleration due to gravity, the entire liquid is at rest at same of all points. Like all points, the pressure in the fluid at rest is same at all points. Whether you assume it from the right side of the container, of the left side, upwards or downwards, any place, any direction. Yes. Then a liquid exerts equal pressure in all directions, as we can make out. Like if the pressure exerted over the liquid is same, then the liquid will also exert the same pressure, just like Newton's third law, action-reaction pair. If the pressure in an enclosed fluid is changed at a particular point, the change is transmitted to every point of the fluid and to the walls of the container without being diminished. It was much probably discussed. Yes, applications of Pascal's law. Like for the hydraulic lift, this kind of apparatus is actually known as a hydraulic lift. For hydraulic jacks, lifts, pressure brakes, etc., pressure is equals to force by area, as we all know. It is profoundly known. And if we are comparing two areas and two pressures, then they should come out to be equal to make it a hydraulic lift. Like F1A1 the ratio of F1A1 should be equalizing to the ratio of F2 and E2. The upward force on A2 is F2, which turns out to be F1 by A1, and where A2 turns out to be A2 by A1 times F1. Bernoulli's theorem. For Bernoulli's theorem, and then we'll be solving one question. So like Bernoulli's theorem is the mathematical expression of the law of mechanical energy conservation, just like potential plus kinetic is equal to potential plus kinetic, initial and final respectively. Bernoulli's theorem is applied to the ideal fluids. Like characteristics of an ideal fluid could be: the fluid is incompressible. The fluid which we are making out is incompressible. Fluid is non-viscous in nature. The flow of the fluid is quite steady. The fluid flow is also irrotational. Yeah. So these are certain characters of an ideal fluid, completely theoretical. What does the statement says? That it says that in case of a steady flow of incompressible and non-viscous fluid through a tube of non-uniform cross-section, the sum of the pressure, the potential energy per unit volume and the kinetic energy per unit volume is all same. That only means that the dynamics of potential and kinetic, which were used in the conservation of mechanical energy when the motion was rectilinear or when the motion was over a banked surface, is now getting considered in terms of fluid, and only the term Bernoulli's theorem is getting used. Yes. So we can say that pressure plus rho gh plus half rho v square is equals to constant. And that's the statement of Bernoulli's theorem. Yes. Two respective areas, two respective pressures, but both equalizing in nature. So work done is equals to delta U plus delta K, where we are subtracting, we are finding out the differences between the two potentials. P1 minus P2 times delta V is equals to delta mg times del H2 minus H1. Is also turning out to be the addition of the two differences of kinetic energies, which are half m V2 square minus half m V1 square. Yes. Taking things common and solving things mathematically, concluding we'll be getting pressure plus rho gh plus half rho v square, which will turn out to be a constant. This equation is the Bernoulli's equation, and it represents the conservation of mechanical energy in case of a moving fluid. Let's consider one of the questions. A vertical U-tube of uniform cross section is containing mercury. It's containing mercury in both arms. A glycerin of column of length 10 centimeter is getting introduced into one of the arms. Oil of density 800 kg per meter cube is poured into the other arm until the upper surface of the oil and glycerin are at the same horizontal level. Yes. So that means the pressure will be, means these two pressure will be same. Pressure of A should be equal to pressure of B, and then hence solving it. Substituting the values, we can get it. We can find out the length of the column. Pressure at A is equals to P naught times 0.1 and for B, we can write P naught plus turns out to be 9.6 centimeter. If we assume this to be the meter. Yes. So the height, the length of the column where we are finding this stipulation to be correct is 9.6 centimeter, substituting the values. Assuming both the pressures to be equal, and only in that case we can find out the values of the concerned terms. This question is actually checking the integration and differentiation part of the respective candidate. We are asked to find the time taken by the water level to reach a height of h by 2 from the bottom of the container. That's the stipulation and that's the diagram. A very derivation based question. Only an aspect of differentiation is getting considered and integration actually. A fixed container of height h with large cross sectional area A is completely filled with water to small orifice of cross-sectional, that means pores you can assume, of area A are made, one at the bottom and other on the vertical side of the container at a distance capital H by 2 from the top of the container. We need to find the time by the water level to reach a height of H by 2 from the bottom. Yes. How are we going to solve this? Yes. We all know V1 is equal to, and the derivation of this particular expression will be done in my upcoming classes. Yes. But right now we are more concerned with using up the result. H by 2 as it has been given in the question, where V2 turns out to be root 2 GH. Yes. Area minus DH by dt, d small h by d. Is equal to area times V1 plus V2 dH by dt. But just substituting the values using great in mathematics. The two velocities substituted. Putting the lower and upper limits as we do in conventional integration differentiation questions, h and h by 2, and substituting numerator and the denominator under root h plus under root of small h minus h by 2, which turns out to be from 0 to t dt will give you time is equal to 2a upon 3 times of small a. Taking things common, we'll be getting under root times h by g. One of the very nice questions which you could imagine to just check your integration differentiation logics and also how you are inputting it into a very terminalizing and compact formula under root 2 times gh. So such problems will be part of my classes. Thank you so much, students. Keep practicing such questions and such derivations. For any queries, please revert to my Urban Pro profile. Thank you so much.